Okay, so hello everyone. Today I'm going to present our topic about the titanium dioxide-based photocatalyst coating on glass substrates for environmental applications. About the titanium dioxide is one of the most widely studied photocatalyst materials because of its excellent chemical stability and strong oxidizing power and low toxicity and effectiveness. So in this presentation, I will focus on the basic photocatalyst principle of TiO2 and about the difference between PVD and CVD. And third part is a microstructure and film catalyst. And four is a wide disposition method strongly influence photocatalyst efficiency. Okay, so about the introduction, TiO2 is the semiconductor materials whose performance is highly depend on the both. And first one is film microstructure and is about the deposition technology. And titanium dioxide is an important photocatalytic materials in this paper. Uh, it's talk about the PVD and CVD, how to can control the films problem. Okay, and our introduction about the basic principle of TiO2 photocatalyst. And when TiO2 absorbs the light's energy greater than or equal its band gap, it means the electrons are excited from the valence bond to the conduction bond. And positive holes remain the valence bond. And these electron holes pairs then migrate to the surface. It's about this one and migrate to the surface. This is a main challenge is electron holes recombination reduces photoelectric efficiency and therefore the deposition structures that reduce the recombination and extremely important. And then I will talk about the what are the difference between the PVD and CVD. So first about the PVD is physical vapor deposition. The general steps involve the three parts. The first one is the evaporation of solid materials, and second is transport of vapor to in vacuum, and third is a condensation on the substrate surface. And about the CVD is chemical vapor deposition. The process steps include the five parts. The first one is gaseous, precious, and second is transport to the substrate and absorption on the surface and chemical reaction, and the final is to remove the byproducts. And about the what are the difference between PVD and CVD. In PVD type, the advantage is the high purity films and low deposition temperature and good control over the thickness and composition. And about the CVD, the advantage is excellent conformality and strong adhesion and precious control of the composition and doping. Okay, so in this paper, introduce the PVD part. It has two different methods, and first is magnetron subtraining. It's two parts, using the energetic ions to bombard TiO2 targets and ejected the atoms deposit on the substrate. And the three advantage. First is a good film uniformity and controllable thickness and moderate deposition rate. And second method is PLD. It's two steps. First is a high energy layers passing ablate target material and forms a plasma plum that deposit on the substrate. And it also have some advantage part. Short material transfer and high film property, and about the denser and uniform film. Okay, and I will keep going to talk about the microstructure and film catalyst about the magnetron sputtering. About the PVD part, the film density and structure is important. PVD films typically exhibit a dense microstructure and columnar grain growth and control the thickness and nanometer scale. But they also have some restrictions about the be amorphous initially and require post annealing to achieve crystalline anatase phase. So in this paper, they talk about the TiO2 and VO2 bilayer coating and compared to the TiO2 only TiO2 coating. They find the TiO2 and VO2 bilayer films was less smooth than the TiO2 film due to the presence of VO2. And this paper also used another one is PLD. In the surface morphology, the rougher surface is rougher surface compared to the CVD, but they also can increase the surface area, beneficial for the photocatalyst, and they also can enhance the abstraction of reactions. In the adhesion property, this method is mainly physical bonding, and it also weaker adhesion compared to the CVD. So about the functional enhancement of the PVD, it has two parts. The first one is a multi-layer structure. It has some effects about improved light absorption and reduced electron hole recombination and enhance the photoelectric activity. And the second is doping and composite films result in improved photoelectric efficiency and better optic property. Okay, so this is my part. Okay.
Okay. Hello everyone. CVD process advantages such as simple equipment requirement and the capability with a wider variety of precursors, enabling the fabrication of continuous, uniform thinking with controllable composition. In the CVD process, the choice of precursor directly determine the chemical composition, structure, and the growth rate of the film. Based on the type of precursor used, CVD can be categorized into the following two major classes: single source precursor and multiple precursors. Single source precursor. A single molecule contains all the elements required to form a film. Under thermal heating or plasma excitation, the molecule decomposes to form the target material directly on the substrate. The advantages include fixed composition, system simplification, lower reaction temperature. The disadvantage include limited flexibility, difficult to synthesize. Multiple precursors. This is the most common form of CVD, where different reactants gases are introduced into a reaction chamber separately. The advantages include high flexibility, facilitate doping, lower cost. The disadvantage including gas compatibility, mixing uniformity.拍摄我没有办法切荧幕我真的没办法，我没有办法切下一页。
那我这边帮你切。
嗯，
这里吗？
有看有
是这里吗？
就是画面没有变了，有看
这里吗？
这边是上页，没有
好，哪一个？
下页
好，可以了。
DVD categorized by pressure, precursor state, energy source, and activation categorized by operating phase. Atmospheric pressure representative is the CVD process conducted at or near standard atmosphere pressure. It offers advantages such as simple processing and a high deposition rate. However, it suffers from relative poor uniformity. Low pressure chemical vapor deposition is a CVD process performed in a low pressure environment. Reduce the pressure, minimize unwanted gas-phase reaction, and significantly enhance film uniformity and state coverage. However, it typically requires higher temperature to ensure an adequate deposition rate. Ultra-high vacuum chemical vapor deposition is the CVD process conducted at extremely low pressures, typically below 10 to minus 6 bar. By combining a higher vacuum environment with chemical reactions, it produces high quality, high purity solid material and thin film. This technique is widely utilized in semiconductor applications growth and narrow width fabrications. Categorized by precursor state. Aerosol acetone chemical vapor deposition involves atomizing solid or liquid precursor into an aerosol, which is then transported into a reaction chamber by a carrier gas to be deposited onto a substrate. If feature advantages such as high growth rate and low cost make it particularly suitable for utilizing precursor with low volatility. Direct liquid inject chemical vapor deposition involves injecting liquid solution pressures direct into the reaction chamber, followed by deposition onto the substrate using conventional CVD techniques. This technology allows for precise control over the precursor injection rate and over high growth rate. Categorized by energy source or activation method. Plasma enhanced chemical vapor deposition utilized plasma to dissociate gas molecules, allowing reaction to occur at a lower temperature, 2000 to 4000 degrees, and increase the reaction rate of precursor. PECVD technology enable growth in low temperature environments, making it suitable for temperature sensitive substrate. This is the primary reason why PECVD is so widely utilized in the semiconductor manufacturers. Metal organic chemical vapor deposition is a CVD technique that utilizes metal organic compound as a precursor to undergo chemical reactions and deposit thin film on high temperature substrate. It is the mainstream technology for growing compound semiconductors such as GaN and GaAs. advantages including high precision, high uniformity, and mature equipment technology. Next， 你可以帮我接下一页吗？The following references are used as examples. Atmosphere pressure CVD. Deficit interstitial boron detected TiO2 sensing of loaded gas substrate, starting from boron as the proper site and the titanium tetrachloride as precursor. The interstitial setting of boron causes change in the morphology of the TiO2 tube and significantly increase the cyclonic and the average particle lifetime. The boron TiO2 tube exhibited the prior photocatalytic properties for the degradation of the salicylic acid and also assists CVD. Deficit TiO2-TiO2 composite film on the gas substrate. The deposition was conducted using zirconium acetaldehyde and titanium isoproposite as a precursor under atmosphere at 4050 degrees. The thickness of the film was close to 500 nanometers. Compared with the TiO2 film, TiO2 composite film show better photocatalytic activity in the degradation of reservoir, which was attributed to the improvement of the surface acidity of the composite film. In addition, there is a high hydroxide concentration on the surface of TiO2 film, which can be used as hole trap to inhibit the recombination of the carrier. 那接下来也谢谢。Plasma enhanced CVD deposition AgMPS-TiO2 composite film on the quartz glass substrate. Originating from AgNO3 and TTIP as the precursor, the addition of AgNPS changed the morphology of the film with the appearance of particle aggregation. In addition, doping a moderate amount of AgMPS could enhance visible light absorption and reduce the band gap, thus exhibiting the significantly higher photocatalytic activity compared with the pure TiO2. Next, metal organic chemical vapor deposition. Titanium oxide, acetonate, and copper acetonate as a precursor at a substrate temperature of 5050 degrees. The coating was deposited on a silicon single particle and acrylic earth, boroaluminum silicated glass substrate. The photocatalytic TiCuO composite coating could be used as a safe cooling surface to induce an active falling activity. The coat glass was immersed in the seawater to evaluate its active falling effect. Marine bifouling field test proof they had seawater resistant properties and show a reduced colonization on TiO2 and 60 TiCuO coating after 38 days. TiCuO composite coating are promising non-toxic falling release film for marine and industry applications. Thank you.